Welcome back, everybody. The topic this week, which is the last one before the Easter break, is to try to wrap up these discussions about autoencoders linked with the principal component analysis. And one of the reasons why we introduced the principal component analysis is that this is a method which is widely used as an unsupervised method. So if you can set up what we defined last week as the covariance matrix or the correlation matrix, and you diagonalize that one, that can be used as a way to reduce the dimensionality of a problem without you knowing beforehand which kind of features are those which are more important or less important. Now, so this is one reason why I brought up the principal component analysis. The other reason is that you can show that an autoencoder, when you use a linear approximation with the unknown parameters, you can show that that one corresponds to a principal component analysis without a kernel. So that means a linear approximation, which I will remind you of some of these things today. So we will use the beginning of the lecture to remind you a little bit about what we did last time. And then we are going to wrap up the principal component analysis theorem. And we are going to run some simple examples, which hopefully can actually visualize what the principal component analysis is doing. And so remember that this is one of these pre-deep learning methods, which were very popular and still are very popular for making a dimensionality reduction. So autoencoders function also as a kind of dimensionality reduction. So the whole idea is that you feed in some data. So autoencoders are also elements of this class of methods, which are called unsupervised methods. You feed in some data, and then you encode this data in some way, which could be a neural network. And then you reduce the dimensionality gradually, and you spit out something which has a lower dimensionality than what you fed into the system. And last week, we showed that one way to think of this dimensionality reduction is through perhaps the most popular linear algebra algorithm, which is called the singular value decomposition. That is a way which we can use as a dimensionality reduction method. Now, when we've done with that, and this is one of the other reasons why we looked at autoencoders, it's not only because it's a popular method for reducing the dimensionality, but it's also a popular method because it links with generative models like variational autoencoders. So we are using the autoencoders as a kind of stepping stone towards what's coming towards the rest of the semester, which are generative models. So if we get time today, we will scratch a little bit the surface of generative models, and then we will dive fully into that one after the Easter break. And the methods we will cover are things like Boltzmann machines, which are also called energy models, variational autoencoders, which is a variant of this. You will also often see that in many textbooks now, people just mention autoencoders in 1 or 2 pages without discussing even the mathematics, and then they jump immediately into variational autoencoders because that's where much of the hype is. So variational autoencoders were introduced back in 2015, 14 something. And that will serve us as a way to motivate what is coming and what is the overarching view on generative models. And there are some examples in the lecture notes with the codes from TensorFlow, which is something I borrowed from the textbooks I'm recommending. And then there's also one with PyTorch, which I often prefer because it's a little bit simpler to actually run PyTorch codes. And there is a simple example on how you can implement your own autoencoder by having your own neural network code. That's just an example. Or you could do that with a CNN code or an RNN code. Now, the data set which we're going to look at that is the exciting one, which you've seen many, many times, the handwritten numbers. So the probably is a little bit boring. So you can actually change that one to something which is called the Faction MNIST data. So instead of the MNIST data, the handwritten numbers, you can just replace that one with fashion_mnist, and then you can look at different ways you can dress up and then see if you can reconstruct your trousers or your t-shirt or whatever. That's also a very popular example, in which you will see in essentially all textbooks. So there is no exception here. No exciting data. Only things you probably have seen before. So just a quick reminder of the autoencoders. There's also a long list of literature here. You probably not have the time to look at all of it, but the textbook by Goodfellow is actually always a good read. And for generative models, I mean, this is probably where we hopefully can start today. Rashka's book has a very brief introduction to autoencoders. I mean, it's just one page, less than one page. And then they jump into variational autoencoders immediately. There are several tutorials which can be useful to look at. Actually, autoencoders are pretty good methods. So the typical way you set it up is that you have this encoder part, which we discussed last time. There could be a function. This could be a neural network. So this produces some output, H, where you feed in some input X. And then you have some undetermined parameters, which you need to determine via a minimization algorithm. And then there is a decoder part where you take this output and then you transform it again. And what we did last time was actually to take what we called a linear dependence. So H was given by this W times the input, like you would do with linear regression, almost. And then X tilde was given by H times V. And then we had a linear model. If we do that, then we can show that this corresponds to principal component analysis. And these are the things which I will just keep repeating a little bit today. And then when we're done with that, we are going to look at examples of the PCA and then the autoencoder examples and how you can set them up. And the typical schematic picture which you will see would be something like this. Now, to bring up a calculation which we did 4 weeks ago, I think that's 4 weeks ago, you may remember this image here, which is a city in Tuscany, actually a beautiful city. I use every possibility I have to bring up this image. Is something I use and misuse. Now, what you can do here, so this image, the original one, is an image of, well, I think it was 256 times 256 pixels. And this is reduced by a singular value decomposition. So just to quickly remind you about what that is. So it's you setting up the image here, and then you can reduce it by performing a singular value decomposition. And you can keep the 5 first eigenvectors, which correspond to the 5 largest singular values. And then you can try to reconstruct the image, and then you see that it is pretty blurred. So in this case, the compression rate is pretty large, and you're downsizing the image. This is the total number of pixels which you have, the dimensionality. And then you're downsizing it quite a lot. But you perform the singular value decomposition on the image. And then you can keep the 10 largest eigenvalues. And this is now something which is getting pretty close to the original image. Keep in mind now that what you've done is simply a projection of your image to a smaller space. And it's getting more blurred out. But when you then do 20, you see now that you can almost read what's there. And then with 100, this looks almost like the original one. So when you do a singular value decomposition, what you have to do then is actually to keep these eigenvectors, or these vectors, these orthogonal vectors, in order to reconstruct the full image. So this is a kind of way to compress an image, which was a very popular method. I mean, till actually convolutional neural networks came on the market. And if you go back to courses on imaging, et cetera, you will often see the singular value decomposition being mentioned. So I'm bringing this up again, in case you forgot what we did last week. So what I want to do now is to actually go back to some of the mathematics we looked at last week and then just remind ourselves of the principal component analysis theorem and how it is being used as a way to reduce the dimensionality. So this is just an example on how you would compress an image with traditional tools, which in this case is just a linear algebra tool. So let's switch over to the whiteboard and remind ourselves a little bit of what we did last week, and then try to conclude this PCA theorem. And when we have done that, we are going to look at some demonstrations of the PCA and how you can think of it, just to get some kind of intuition. And then we are just using the PCA now to demonstrate that autoencoders with that simple linear transformation corresponds to the principal component analysis, so that you get a feeling of the mathematics behind an autoencoder. Now, when you replace this simple linear behavior with a neural network, then you lose a lot of this simple mathematical explainability. So I hope you see the kind of pedagogical approach to it, so that you can see that an autoencoder is actually reducing the dimensionality of your problem. So let me quickly remind you of the way we think of these autoencoders. So we had some input data, and this is the data we need to compress. And you can think of this as unsupervised learning. So the data does not need to be labeled. When you do a PCA analysis, the data is not necessarily labeled. So you have an input X, and then you have an encoder part, as we discussed last time, where we have a function, and this can be a neural network. So we get an output from this function f, where we have a set of parameters w. And what we could do is to make a linear approximation. And this is the one which links us directly with PCA. So you can use in PCA, you're not limited to a linear approach. If you go into any textbook on the principal component analysis, you will find tons of tricks and transformations like a kernel principal value approximation, where you can actually transform the data with more complicated functions. And I'm going to show you how you can actually think in terms of something more advanced than just a simple linear approach. So we could set up something like W times X. So W is now a matrix, and X could be a vector. It doesn't need to be a matrix and a vector. It could be a more complicated object. And then we had the decoder part. And that gives us now a value X, which is the output. So we have the decoder part is given by this function, and we have some unknown parameters, which we just call V. And if we again use a linear approximation, then we would have this X given by V times this intermediate calculation H, which then transforms into V times W times X. And then the holy grail is to optimize the reconstruction error. And the reconstruction error is something which I'm just going to label like this. So these are the data points which we have. So we are summing over all. Well, let me just write it in a more compact way. Sometimes it's better to write it like this. So we would have X minus X tilde. And often you use a norm 2 or the mean squared error. And this is the quantity you want to optimize. So you obviously want to have a reconstruction error, which is as small as possible. Now, in our specific case, this is something which we can write out as this X minus, and then we have V times W times X squared. Now, what we are going to show now is that this is the same as performing a principal component analysis. So we discussed that partly last week. And one of the approaches which we looked at was us linking this with an ordinary least squares. So I wanted to remind you of some of the things we went through last time. So this is the quantity which we now want to optimize. And we would obviously like to have that as small as possible. What you could say then is that you, instead of optimizing this difference, you could then maximize this quantity here. That's another possibility. But let's now just quickly remind ourselves of the things which we did last week. So we had the a matrix X, which we call the feature matrix or the design matrix. So this is the link with ordinary least squares. And this is a matrix where we had vectors x0, x1, up to some feature xp minus 1. And these vectors are not necessarily orthogonal to each other. So we can actually have correlations. And then we defined the covariance matrix, which we often write as a sigma. And that was, and in this case, is a sigma x here. And this is given by 1 over n of x transpose times x. And this is given by, normally, we would just write it as an expectation value of this quantity. Now, pay attention now that this is a matrix. If you look at the single vectors, you would have to write for single vector, you would actually have to write that as an outer product of vectors. So this quantity is a matrix, just keep that in mind. And that has dimensionality p times p, which are the number of features. So the matrix X itself, this matrix which we have, has normally a dimensionality of n times p. Now, what we could do then is to perform a singular value decomposition. So with the SVD of this quantity X, we could write this out in terms of an orthogonal matrix, U, a matrix which contains the singular values, and then a matrix V, which is another orthogonal matrix. So this matrix is, so X, so U has dimensionality, just quickly, this is just a quick reminder of what we did last time. D has a dimensionality of n times p. And if you've been able to write it down, I'm just going to move to the next page. And this V has a dimensionality of p times p. And these are orthogonal matrices. Actually, I shouldn't write it like that. So this is the diagonal matrix, n p times p. And then we have a U of ut is equal U transpose of U. And that's a unit matrix of dimensionality n times n. And this matrix D contains the singular values. So I'm just reminding you of some of these properties. Up to sigma p minus 1, and then it has zeros on the rest here. So we say the rank of D is p. And these sigmas are ordered so that they can be given by a descending series or an ascending series. That's up to you. So there is no kind of a specific thing with the way you order these singular values. And these are larger than 0. So the matrix which we typically feed in, this feature matrix, can be singular. We don't know that. Normally you can have correlations between the different columns. If you're lucky, there are no correlations. So one of the things which we can do then, and which we did last time, is that if we take this matrix sigma, so this is normally written as the covariance. So let me quickly remind you. So this sigma would be the covariance of the matrix X. It's common to divide that by the variance. So that means that along the diagonal, we just have ones. And what we found last time is that the eigenvalues and the eigenvectors of this matrix sigma, so sigma x, when you diagonalize it, so that means that we would simply then take a unitary transformation or an orthogonal transformation, and this will become a diagonal matrix, which we call sigma y. If you find such a matrix, S, then you would then get along the axis here, you would get the variance, sigma 0, and then var, I should make a little bit better space here. Let me just move it down to the next one. And these were the things which we discussed last time. So I have a y0 and var of p, yp minus 1. So this matrix is a p times p matrix. And we have 0 here. And these variances, y of I, so this is a diagonal matrix. So remember now that we are, the matrix S is a non-stochastic matrix because we have a deterministic algorithm to perform a transformation. If you're thinking of Jacobi's method to diagonalize a matrix, that means you just have cosines and sines, and you choose these angles so that you zero out all the non-diagonal matrix elements. So that is a deterministic recipe, and that doesn't enter an expectation value. So sigma, which you have here, is an expectation value. It's a covariance. It's a matrix. So when you diagonalize, you get obviously a diagonal one. And in that specific case, this is given by the singular values squared. And these variances go from y1, y0, and this is ordered so that it's given by y1, etc., up to the variance of y of p minus 1. And these are given by the squared as we showed last time. Just let me quickly remind you of that. So if you look at that matrix sigma x, so sigma x here is nothing but 1 divided by n multiplied with this matrix x times x. And then we use the singular value decomposition. And then we could show that this matrix is nothing but 1 divided by n times v multiplied with this matrix v squared times v of t. So what I can do now is to multiply with v on both sides from the left, no, sorry, from the right. I still struggle with this difference, left and right. So if I multiply from the right with v, we can then use the orthogonality of these matrices. And then we get that sigma of x times v is the same as this 1 over n. And then I have v times d squared, which again led to sigma x multiplied with one of these vectors, which was 1 divided by n, and it's actually sigma I squared times v of I. And this matrix V is just the set of orthogonal vectors of V of P minus 1. So the using the covariance matrix and diagonalizing that one, you can perform a dimensionality reduction by just keeping the largest singular values. The largest singular values define then the variances. Actually, I forgot one small thing. So this should be divided by n here. I forgot that one. So the one way to apply the principal component analysis is to use the singular value decomposition. If you go into the literature, this is often called the geometric approach. Geometric because you're using linear algebra and you're looking at the way you transform vectors. So I'm going to show you some simple examples later so that you can build up an intuition here. on how you can reduce the dimensionality. So if you look at these quantities now, what you can then say is that if I now simply look at these variances, so this is the same as the variance, and these variances are quantities which I can use to truncate the dimensionality of the problem. So what I could say now is that I could define a reduced space where I have a dimensionality which I'm just going to call D. And that means that I'm going to sum, and this D is assumed to be smaller or equal than the rank of the correlation matrix or the covariance matrix. And then I'm going to make an approximation where I have a sum up to D minus 1 of the variances, which are now just the diagonal elements here. And I can now assume that this is smaller than a given number, lambda. And that lambda could be, as an example, it could be 95% of all the variance, of total variance. So the total variance is the sum of all the diagonal elements which you have in the covariance matrix, sum of total variance. And the total variance is nothing but the sum from I equals 0 up to P minus 1 of variance of gamma of Y. And that is the same as the sum from I equal to 0 when we use the singular value decomposition, sigma I squared divided by n. So the standard way of performing the singular value decomposition is actually to set up the covariance matrix. You diagonalize it, and then you look at the eigenvalues, or the singular values as they're called, which are again the same as the covariance. If you divide this quantity by the variance, then you're diagonalizing the correlation matrix. And many people prefer to do that because the variance itself can become a large number. If you divide it by the variance, then it's scaled to be 1 along the diagonals. And that is much simpler. So what you would do then is simply to keep a given number of eigenvectors, like I did with that decomposition of the picture from that town. I just kept, let's say, the 5 largest eigenvalues or the largest variances, and then I went to 10, I went to 20, etc., and you saw that I could reconstruct the image better and better. So this is the standard approach, and it's a way to reduce the dimensionality of the problem. You don't know this beforehand, what you're doing, in the sense that you don't know how big that D should be. So this is something you have to play around with. But suppose now that you accept that you reproduce only 95% of the total variance, then you can use this D as an effective degree of freedom. So if P was a 10,000 and D is 10, then you have only 10 features. But keep in mind that these 10, they are linear combination of all the 10,000 you have. So when you're then analyzing these eigenvectors, you have to look at the components in front of the eigenvectors. So if there are some few eigenvectors with large components, when you square this, that tells you the probability of being in that specific state. If you have, let's say, these 10 components give you close to 100% of the probabilities, then you would say that these 10 components represent some specific features, and these are the essential features. So going back to that trivial housing price example, which I gave you, suppose you have something like 20 features which label a house, and then you want to find how correlated these features are with the price. You know that if you then diagonalize this 20 by 20 matrix, and you have a feature like the number of rooms, you would expect that to be important for the price. If you look at the number of bathrooms, that could be important. If you look at the size of the house, that is probably important, and so on, the size of the garden. So these would be features which could be dominant if you look at the final price. And you could say that now I can fit the final price in terms of specific features. If you have another feature like the number of chimneys, that is probably not that important for the price. And then you could just leave that out in determining the price. So this gives you, it's a way to obtain effective degrees of freedom. So with a singular value decomposition, this is pretty straightforward to see. But let's look at this statistical way by which this method was developed first. And the first time this was presented was actually in 1903, I think. So it's a very old method. So let's just look at the theorem and just state it here and then prove it. So the theorem, PCA, the statistical approach to the PCA theorem. Oh, by the way, before I do that, let me just say quickly how this relates to the calculations which we are doing now with autoencoders. So suppose now that when you do this dimensionality reduction, D is just equal to 1. That means that there is only one eigenvalue which dominates. Suppose you say that you want 95% of the total variance. And there is actually one eigenvalue which gives you that. Then you would say that there is a dominating vector, which we would call V0. Okay? So if we then go back to the reconstruction error, what we know is that these vectors are actually, we know that V0 by construction are equal to delta 0, 0, just a Kronecker delta. We know that they are orthogonal by construction because we did the singular value decomposition. So when we then look at the reconstruction error, which I label as this J of X, the way you can write this now, over all the data which you have, is as the optimization problem of X minus, and now I have to make a matrix. So this is my V times V0 transpose. Remember that V is a vector, V0 is a vector. If I want to make a matrix, which now takes my X and maps it into this X tilde, so this is the reconstruction error. If my variance now is 95% of the total variance for only this state, it means that this should give me a pretty small reconstruction error. So the way the original PCA was developed was actually to assume that there is an orthogonal set of vectors, which we then can use to define such a projection of the full data. If you go back to the ordinary least squares, then we could show that this was given in terms of the vectors from the matrix U. We had a perfect projection of the original value X into a smaller value X tilde. So this is now something you can think of as a dimensionality reduction in the sense that instead of having the full set of features, which are given by this number P, you have a smaller dimensionality. You see the basic approach here? So the way the PCA was developed was to imagine that you have such a basis and that you can project down your original X and then reduce the dimensionality that way. So here we have only one feature, one of the orthogonal vectors. Instead of having 10,000 features, we have only one. And then your hope is that this one is going to be as small as possible. So then we are minimizing this problem here. Or eventually we are maximizing this one. That's just equivalent types of problems. And if you now look at our link with autoencoders, and with a linear approximation, what we had then was a reconstruction error, which is X minus, and then we have V times W times X. So what it means then is that these matrices multiplied with each other, they are the same as the one which I built up here. So you see the connection between the linear approach. I get a matrix, which is now given in terms of these orthogonal vectors. And that matrix plays the same role as the two matrices which I have here. These are just two matrices. So I could then just interpret them, these two matrices, as this outer product of these orthogonal vectors. So with the SVD, we have it. And if the variance is 95%, and we are happy with that as a truncation, then we can just use this D equal 1 as an effective degree of freedom. Okay? So I hope you see this is basically the overarching message. When you replace the linear approach which you have here with a feed-forward neural network, then this simple mathematical and pedagogical link is gone, because a neural network, as you know, it has lots of non-linearities, and then we cannot make this kind of simple comparison between these. But you see essentially what we are doing now by introducing these matrices is that you can think of these matrices as a dimensionality reduction, as we did here, of the full problem. Yeah?
You state that V and W should sort of optimize to be inverse to each other, because then we're saying
so that's the way the original theorem was developed. So you actually put up a Lagrangian, which we started to scratch the surface of last time, and then you can build up through that. Then you can build up a set. You can actually build up all these vectors. And the thing then is that these vectors, when you do this build up, you can actually show that these vectors have as eigenvalues the variance of the covariance matrix. And that's a very powerful link. So that means that you can actually start with this covariance matrix, and you can gradually reconstruct by an optimization problem. You can reconstruct all these vectors. So as I said, the geometrical approach with the singular value decomposition gives us this immediately. But the singular value decomposition was not invented in 1903. And that's how you actually went through this machinery to build up this orthogonal basis. So let me just show you how you can build up the orthogonal basis. And then this basis will have as eigenvalues the variance. Okay? So let's look at the statistical approach to the principal component analysis. And this was actually, I think it dates back to 1903 or even before that. As I said, with a singular value decomposition, life is much easier. And because then we just do it. Now, what we are going to do now is to go back in time. And this is something you can just see as a curiosity nowadays. I mean, you won't do this because the singular value decomposition is much more efficient. So the theorem here, and I'm going to spell it out. So we assume that we have a vector x. This could be our input data. Vector x has its principal component as, so I need to write down this stuff here, has its principal component which can be computed from the eigenvectors of the correlation matrix, or the covariance matrix, computed from the eigenvectors of its covariance matrix. So be a little bit careful now with the definitions which we've been having, because now we are dealing with a vector. So this is the expectation value. And since X is a vector, we need to take the outer product of the vectors to construct the covariance matrix. So when I had this matrix X, so just keep in mind that previously I used the vector matrix. This is a matrix. So if I do this with vectors, I just get a number. So what I want now is to set up the covariance matrix for the vector X. If I take the inner product, that's just a number. What I'm also going to assume then is that this sigma X has obviously has positive eigenvalues, which is the definition of a covariance. Then what we have then is that the first D, so if this is a dimensionality, principal components. And keep in mind also that I have centered the results. So when I look at the number X, one of these entries, I have subtracted the mean value. So these are typically quantities which then have zero mean value. This is pretty common to do that. So this would be the first principal component of a zero mean multivariable random variable. So these are random variables. We don't know what kind of distributions they follow, but the X's are random variables. It's a multivariate random variable. And we also assume that we have taken away the mean value. So these are centered data. So then the first D, principal components of a zero mean value. So this is multivariate random variable. X, where Y, where we have defined with. And these quantities Y of I are going to be the variances. 0 up to D minus 1. And then I have that this Y of I is just given by this vector U of I times T times this original vector. And where this U of I with I equals 0 up to D minus 1, they are orthogonal or orthonormal vectors. Now, this quantity V of I is going to be the same as the variance, which we have discussed before. So these are orthonormal vectors of the covariance matrix X, which is now this expectation value of this vector X times its transpose, which is just an outer product. And this is associated with its largest, its D largest eigenvalues. And I just labeled these eigenvalues with a sigma of I. And this sigma of I is actually going to be the variance of this quantity Y of I, which we defined earlier. And the assumption now is that there is such a set of vectors, which then optimizes my reconstruction error. So this is essentially the theorem. We assume that there is a vector X, which has a principal component, which can be computed from the eigenvectors of its covariance matrix. And that is given by an orthonormal basis set. And the proof assumes that first, you can actually assume that the covariance matrix doesn't have repeated eigenvalues. You can show that this applies also for repeated eigenvalues. And what we want then is that the variance, if I now look at the variance of, so let's just write down the proof here. So if we look at the variance of a transformed vector of ut times x, so this variance is actually given by, so keep in mind that x is centered in the sense that I've subtracted the mean value, so I don't need to subtract the mean value. This is the same as the expectation value of this ut of x squared, which then is the same as this quantity here of ut of x, x transpose of u. Now u is an orthogonal transformation, which means that this is non-stochastic. So there's not stochasticity here. X is a stochastic variable. So that means that these do not enter an expectation value. So I can rewrite that one in terms of x transpose times u. And that is nothing but u of t times the matrix here. And if this diagonalizes the problem, then what we have is a diagonal matrix. And so this actually brings it over to a diagonal form. And this is what we would call a sigma y, which just has along the diagonal, it has the variance of y0, etc., all down here, and then 0 z's. So what we're going to do after the break is simply to show that by optimizing these eigenvalues or maximizing them is going to correspond to the same as minimizing the reconstruction error, and that these eigenvalues which you have are going to be the variances. And if we just keep the largest eigenvalues, we can then gradually construct this set of eigenvectors, one after the other one. So this is what we're doing here, is to introduce, which we'll do after the break, a Lagrangian formalism. And with that Lagrangian formalism, we're actually going to reconstruct what we get with a singular value decomposition by diagonalizing the covariance matrix. And this was the way the PCA was demonstrated more than 100 years ago, before the singular value decomposition was invented as an algorithm. So the singular value decomposition, I should say, is my favorite linear algebra algorithm. It's always been. Okay, I'm gonna stop the recording and then we take a break. So what I'm gonna do now is simply to prove this theorem by constructing these vectors. And then we are going to dive into some simple applications to a 2x2 covariance matrix, where we can actually see immediately whether we can skip 1 degree of freedom or not. The strength for the PCA is obviously that we don't know how many degrees of freedom we need to keep, because we can typically have thousands and thousands of features in our data set. And then we don't know a priori which one is the one I can leave out, or which ones are the ones which I can leave out. So hopefully the simple application will also give you the possibility to develop some intuition about what the PCA is doing actually. So let's just go through some of these details and try to wrap up this part. So what we typically do then in the proof here is then to set up an optimization problem where we can optimize the largest eigenvalue. So the typical the way it was developed more than 100 years ago, optimization. This was to maximize the eigenvalue. So we assume that this vector u0 transforms the covariance. And this vector u0 has a specific dimensionality. And this is subject to ST, subject to requirement that this should be orthogonal and normalized. So these are the typical requirements which are put in. And what people did then was simply to set up a Lagrangian. So Lagrangian calculus had been introduced back in the 18th century. So you would simply optimize a problem of this type here, of u0, and then you have a Lagrangian multiplier, which is 1 minus u0 of u0. And then you take the derivative with respect to u0 and lambda 0. And then you put these derivatives to 0. So that is the optimization part. And I'm assuming that people are familiar with the Lagrangian formalism, which is often used as a way to optimize problems subject to a constraint. So some of you may have met the so-called support vector method, which is a popular machine learning method. And that defines a Lagrangian where you have some specific constraints which you have to fulfill. So what it means then, when you take the derivatives with respect to u0 and lambda 0, and then you put these to 0, then you get two equations where you have one, sigma 0 of u0 is given by lambda 0 u0. So that's an eigenvalue problem. And then you end up with the other one when you take the derivative with respect to lambda 0, you simply have u0 equal to 1. And that follows by taking the derivative with respect to lambda 0, and that's pretty obvious, because then you have 1 minus u0 transpose times u0 has to be equal to 1. So what you find then is that these are now the eigenvectors and eigenvalues. So this lambda 0 is then nothing but the variance of the first term, which we call y0. Then you can construct the second principal component. And what this does when you're setting it in, it's an optimization error and a reconstruction error, where u0 is now the eigenvector with the largest eigenvalue of the covariance matrix. Then you can construct the next one. So the second principal component. So we call this the first principal component, u0. And in the second principal component, we then define a new vector, ui, and this has to be orthogonal to u0 by construction, because we want, so in essence, what we are doing now is to use the Lagrangian formalism to build up all the eigenvectors and eigenvalues of a matrix eigenvalue problem. So it's just an alternative to actually an eigenvalue problem, solving that one. And then we would have a new optimization problem where we have to find what we want now is actually that the variance should be of u0, and the other one, we want that to be 0. So what we want then is actually that we want to optimize this problem of sigma x of u1 plus lambda 1. So this is the next eigenvalue, 1 minus u1 of t of u1. And then I have plus a gamma of u0 of t of u1. And when I take the derivatives, now I have three parameters. I have u, the unknown vectors. I have defined the previous one, u0. I need to define lambda 1 and gamma 0. So when I take the derivatives and set them to 0, with respect to, and then I need the derivatives of u1, of lambda 1 and gamma, I'm getting the following equations. I get a sigma 0, a sigma x, plus a gamma divided by 2 of u0, and this is equal to lambda 1 of u1. Then I have the other equation, which says that these guys have to be orthogonal. And finally, I have the final equation, which says that u of t of u0 is equal to 0. Now, then I take this equation here, and I multiply with u0 transpose. If I do that, then I have u0 transpose times sigma x. This is also an eigenvector of sigma of x. So this gives me actually lambda 0 of u0. And this is multiplied with u1. From the conditions which I have shown that this is 0. So that means that this quantity has to be 0, plus gamma half of u0 transpose times u0. So this is actually equal to 1 as we define, and this is equal to lambda 1 of u0 of u1, and this is equal to 0, and that simply leads to gamma having to be equal to 0. So then what I find, if that is the case, what I find then with this, let's see, everybody's done here. This simply leads to sigma x of u1 is equal to lambda 1 of u1. And that means that if I multiply with u1 transpose, that means that this variance of y1 is simply given by u1 transpose times sigma x of u1. So when I did the singular value decomposition, I had these vectors, and they were given by the vectors v. So what I'm doing now is simply actually to reconstruct what I had. So in general, what I end up with is the following equation, which I need to solve. So I have a u of t times a sigma x of u of I plus a lambda I of 1 minus u of I of t of u of I. And then I have to make sure that these solutions are orthogonal to all the previous ones. So this would go up to some I minus 1, and then I have a gamma of j of u of I of t of u of j. So these will be all the previous vectors which I found. So the thing now is that when I now maximize this reconstruction or this set of vectors, what I get is that this is a variance. So the basis which I find, these orthogonal vectors, correspond then to vectors which are eigenvectors of the covariance matrix with the specific eigenvalues of the covariance matrix. And then I can construct this so that these vectors become smaller, these eigenvalues become smaller and smaller. So what I want to do now is to switch back to the Jupyter notebook, and then we're going to look at some simple examples and the basic algorithm, the PCA algorithm. So keep in mind that the reason why I brought this in, or brought this up, is that I wanted to make the link with an autoencoder when I have a linear encoding and a linear decoding. Then you can see that an autoencoder is doing an explicit dimensionality reduction. The way you would set it up, if you use a neural network, you could have this incoming value, the incoming vector x, to have a dimensionality or length of 1,000. And you could require that the outgoing one has a length of 10. That would be your dimensionality reduction, which you could plug in by setting up a given number of input nodes in your neural network and a given number of output nodes in the decoder part. And then the encoding part and the decoding part will take care of this dimensionality reduction. And this is typically the way you would set up a neural network, or if you're doing a convolution neural network, that is also a way of performing a dimensionality reduction. So let's switch back and see if we can develop some further intuition about this type of problems. So let's go back to the Jupyter notebook. Not that one, but the one for this week. So let's scroll down a little bit. You will find more of these details. So the way you would now set up the algorithm typically, so you would set up the data points for the design feature matrix. This is a typical approach. And depending on the number of features you have and the type of problem you want to reduce the dimensionality of, this matrix can be small or it can be huge. A typical example, if you're doing research in bioinformatics and you're looking at the DNA of or some DNA properties, you can have something like hundreds of thousands of features. And perhaps only some few of them are relevant for a specific type of cancer. But you don't know that beforehand. So this is the first thing you would set up. And then typically you center the data, which as we discussed last time. And that leads to a new matrix, which I call X bar. And then you would compute the covariance matrix, you set it up. You find the eigenpairs with the eigenvalues. So you can simply diagonalize that matrix. There's nothing which hinders you to do that. Or if you want to do the singular value decomposition, you could do that. But a singular value decomposition requires normally twice as many floating points operations as an eigenvalue problem. So there's always this kind of cost here. And then you order the eigenvalues in order of decreasing or ascending. Normally it's decreasing. And then you keep only those L eigenvalues larger than a selected threshold values. And then you discard P minus L features since you expect small variations in the data. This is the PCA in essence. It's pretty straightforward, right? And actually, my advice, if you can, calculate the correlation matrix, because that's before you do anything with the data. And one of the reasons for that is that tells you quite a lot about which data are most correlated or not. And it's a useful thing to do because it gives you a deeper insight about the data. So I always calculate the correlation matrix before I do anything. If you can diagonalize. So the example here is actually an example where I've now put up a correlation matrix where if you diagonalize this one, so I'm just setting up. So I have a mean value here. And I have decided now that if you look at these quantities, there are strong correlations because the values are close to each other. So you can see that immediately. So suppose now that when I construct X, in this case X, we just have two vectors. So remember now that my correlation matrix, I can have, if you look at this matrix here, the X matrix, I can have thousands of data here. So in my case, I'm going to have just two features. And that's why my covariance matrix is a 2x2 matrix. So here I just made it up. But then I assume that I had some basis of thousands of points here. And then when I'm doing this, so you can see now this is essentially what I'm doing. So I have a set of data points. I am forcing this to be a multivariate normal distribution where I have two features and I force it to have this mean value and this covariance. Okay, so I'm producing these 10,000 random numbers, which will be the 10,000 rows here, but I force this to have a specific covariance and a specific mean. Okay, so you can always decide when you call a normal distribution or Gaussian, you specify what's the variance and what's the mean value. And this is what I'm doing here, except that now I have a multivariate distribution. So if you do that, so let's do that. Then what I'm doing, I'm centering the data. So these are the basic steps. So when you set up the correlation matrix, you could actually do this. So I'm using pandas, and then I subtract the mean from every column. And this is just pretty straightforward. This is just one of the tons of ways of doing that. I've centered my data. I'm going to print out my covariance. So I don't get exactly 4, and I don't get exactly 2 here because I have only 10,000 data points. So when I call my distribution, I will not get exactly what I defined. So if I were to include 1,000,000 points, I would get closer to 4 if you look at the original matrix. So this is what I plug in, but since I have only a limited number of data, I don't get exactly 4 and 2 when I calculate these quantities. Okay? Then what I'm going to do now is simply to extract the relevant columns from the center design matrix. I'm calculating the covariance, and now I'm printing my results. So this is what my data set looks like. So I have two features. You could think X1 here and X2 here. So if you look at this, and I say, these are your data points, right? So 10,000 for x0 and x1. And I plot x0 and x1. So this is just a two-dimensional plot. If you look at this figure, would you say something about, would it be reasonable here to discard one of the degrees of freedom when you just look at it as it stands? What is your feeling? So now you're looking at the figure and you say, I want to use this figure to get rid of one of the degrees of freedom. You have only 2 degrees of freedom, right? So what does this figure say actually? Is that reasonable? There are, yeah, what you would see also is that you have if you go along one of the axes, you have a big variation in one of the data, and you have a big variation in the other one. So let me make a change now and see if you can develop some intuition, because this is a case where we have just 2 features. And when you have 2 features only, what you do is that you plot. And then you can, from the plot, you can say something about your data. But if you have a million features, you cannot make a plot, right? Then you have to do something which is unsupervised, like PCA. So here, humans can actually go back and, okay, so let's just do another example, and let's now change this. And now I'm going to change this to just put 20, and I put 0.2, and let's do 0.1 here, and then 0.1, and I do this 0.2. So let's rerun now. So let me just rerun. What does your intuition say now? Can I get rid of one of the degrees of freedom? You could. I mean, the one along the y-axis, you have very small variance. Most of the variation happens along the x-axis. So I could say now that I can just leave out this degree of freedom along the y-axis. I mean, this is the kind of way you can think. So you see, what you see here is that a PCA, in this case, you could say that most of the variation happens along the x-axis. So this, when you diagonalize, this will be the largest eigenvalue. And you see that when you look at the eigenvalues here. That's where you have the biggest, when you diagonalize this quantity. So this is your covariance matrix. When I diagonalize, these will obviously be 0, the non-diagonal ones. But this will be something like 20, and this will be a very small value. Yeah? Yeah.
But it's not divided by the variance, no?
It's not, you could divide by the variance, you could do that. But then you would diagonalize the correlation matrix. Yeah. Yeah.
Maybe, yes, one of the variable has a big
yeah.
bias, but maybe the epsilon is much more related to the small bias.
It could be, you don't know that, because normally you would diagonalize the covariance matrix, just gives you the variance in one of the axes, right? So the way you would use this is simply to say that I don't have big variations along that y-axis. So I could think of that as a degree of freedom I could reduce because it would have a small variance.
What if the degree of freedom is much more?
Yeah. No, because in this case, but this would be just the data which you feed in, right? As you saw. And now I'm asking myself whether, when I want to reconstruct this, whether it's sufficient to just keep one of the degrees of freedom and skip the other one. So that's the question I'm asking now. So when I diagonalize this matrix, that will obviously be diagonal. And there will be 2 orthogonal vectors, right? So there will be one vector along the plane here, and one which stands orthogonal to the other one. So they will separate. and they are no longer correlated when you diagonalize. So when you are taking the correlation matrix or the covariance matrix and you have diagonalized, then you have only diagonals, and then you're taking away the correlations. So the original matrix shows that there are correlations in the data. When you diagonalize, then they are uncorrelated because you found a set of orthogonal eigenvectors. So what I found here now is that there's an eigenvector in this direction, mu0, and one which is orthogonal to that in the plane. But the one which is orthogonal plays a smaller role because that will have a small variance. So in my reconstruction of the data, I could now say that I take away that degree of freedom which comes from the second component. So you have to think of this as a matrix you are diagonalizing. And when you diagonalize it, then the new data which you have is uncorrelated. The original one is correlated. And that type of information which you see here is actually, this one is important because that tells you the degree of correlation in the data you had originally. But when you now diagonalize, you have found an orthogonal basis which allows you to transform away some degrees of freedom. So I think that's the answer to your question because the original matrix is correlated. Yeah.
It's the sum of the eigenvalue.
Yeah.
Let's say you added the set dimension to it.
Yeah.
And it still just goes on the x-axis.
Yeah.
It has no relation to set.
Yeah.
That means that this would have the largest.
Yeah.
Eigenvalue.
You see now, if I diagonalize this matrix, this eigenvalue will be close to one order of magnitude larger than that one. So if you diagonalize this one, you would have 20 plus 0.2 something. And if you then say, now I want to truncate my total variance, when you sum the two elements, then you could say that now I truncate it to only 90%, and then it will be only one which dominates. And that is you manually taking away a degree of freedom. So the figure which you see here shows the correlations because you see that it's not flat around, it's not fully flat, but it tells you before you do anything that there is a possibility for getting rid of one of the degrees of freedom because one of these has a very small variance and it doesn't fluctuate much. So you don't make that big error in predicting the second degree of freedom to basically be around zero because it has been centered, right? Did that help a little bit? So this is the visualization you can make before you do anything. And these kind of visualizations are extremely useful if you can do them. But when you have more than 10 degrees or many degrees of freedom, it's very difficult to see. I mean, at least when I am in three dimensions, I'm lost. So, and that's why you automatize it and you look at the eigen vectors, which are the variances, and you simply put a cutoff and say, I just skip what is beyond that specific line. So this image is before you've done the diagonalization and taken away a component. Yeah. Yeah, yeah. So what I've done is that the basis I'm producing should be orthonormal. That's the only assumption I've made. Yeah. No, I haven't done that. But normally what you want is actually to minimize the reconstruction error. Yeah, 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 exactly. Yeah. Okay, let's, so in the slides, you will find other things you can play around with. So the typical approach is that You would as I said, you diagonalize the sample covariance matrix. Typically, you can use a standard diagonalization. I guess this is not that important. So if you collect all the steps here, this code here actually does everything. And if you use scikit-learn, which is a very popular library, you can then simply decide to reduce the matrix in terms of specific components. There is a scikit-learn function if you're using scikit-learn as a library, which simply does PCA, and you define the number of components you want to keep. You can put in a cutoff if you want to, etc. So these are just simple examples, and which I invite you to take a look at. I'm not going to go through all these details, and because I wanted, so this is basically what we went through on the whiteboard, and there are several small examples on how you can use it to define how many components you want to keep, etc., etc. And then there's also an example here on a data set which contains 30 features. So this is a simple example where you can do logistic regression on the data set. So there's a famous data set on breast cancer tumors from Wisconsin. There were roughly 500 patients, and this data set has something like 30 features. The features could be something like the surface area. If you make a thickness, you can measure the thickness of the tumor, etc., etc. And these are all features which are used by pathologists to determine whether this is a benign or a malignant tumor. And then the pathologists have their expertise, and then they would simply put 0 and 1, whether this is a benign or not benign tumor. And the features are typically things like that. I think they have also the color of it, the thickness, surface area, etc., etc. So these are typical quantities. And here you can do a PCA, and you can keep only 2 components. And if you run that calculation, what you would require then is that you keep only 2 of these components, and you can see now the train set accuracy. So this is the training which you do with logistic regression. So this is with a train set. When you have scaled the data, it gives you a 99% correct classification. If you keep only 2 of these components, you get a classification or a classification accuracy of 96%. So that means that 4% of the cases are wrongly classified. So if you're happy with 96%, and this reduces your dimensionality, then you could use that as your effective degree of freedom. Now, in the slides here, you will also find, I'm not going to go through everything here, because there are many ways of doing the PCA. But if you go back to the autoencoders, there's one example where I use TensorFlow, and it's all on the MNIST data. You can actually replace, I can bring this up, but I wanted to show how easily you can do this with PyTorch. So in PyTorch, I'm taking this MNIST data, so the data set MNIST, is 60,000 handwritten numbers, so numbers between 0 and 9. And actually what the most of the time is, most of the code is actually on you reading the data and plotting the data. But the autoencoder, if you scroll down here, so these are the typical data, contains now one dimensionality reduction. So I have the input has 784 input variables. So these are the pixel of an image. So the images are 28 times 28. And then I reduce this to 128. So this is my dimensionality reduction. And when you're setting it up now, you see now I have a feed-forward part here, which is the encoder part. So I have a linear here. It's actually a feed-forward neural network. And I put in the dimensionalities of the inputs. This is the dimensionality, the number of nodes for the hidden layer. I do the same here. So I have a new neural network. So I'm actually stacking together 2 layers here. And then I do the same with the decoder. So it's still a neural network. And then my decoder has reduced the dimensionality to 128. And then I want it back and compare it with the 784 which I had. So I define a decoder and the model which I have here. So that contains the autoencoder part here, contains now the decoder and the encoder, which are just neural networks with a given number of hidden nodes and a given number of input nodes. So this is something which you can actually set up with your own feed-forward neural network and repeat the same exercise. The example above uses TensorFlow, but it's basically the same philosophy. So TensorFlows and Keras, I just invite you to take a look at these examples. And in both cases, the kind of setup is you defining the encoder part as a convolutional neural network, a standard feed-forward neural network, or a recurrent neural network. In our case, we linked it with PCA to demonstrate the dimensionality reduction. Here we're just using a neural network to spit out less outputs than we had as inputs. So it's as simple as this. It's actually not very difficult to set up your own autoencoder. So it's always a little bit boring to actually go through all this stuff here. Here I define the type of loss functions which I want. I actually use the MSE. I use this Adam optimizer. So these are things which many of you are pretty familiar with. And then do the training, calculate the loss functions, and then you can start looking at the outputs which you generate and how good they are and not. And then you can calculate the final reconstruction error at the very end. And in this specific case, the reconstruction error is not something you would brag about. It was something like a 65% recognition, which is not very good, but I've actually reduced my dimensionality considerably. So this is this autoencoder part in a way is you stacking together neural networks or standard deep learning methods. You can make this decoder and encoding part deeper and deeper. So it's up to you how much time you want to spend on the training. And then you would still play around with the same way as you do in a neural network with setting up the different parameters. So there's nothing different from that. And then you could obviously set up a linear encoding and decoding and compare that with PCA, and you should essentially get the same result there. So as I said in the beginning, I'm going to use this as the stepping stone towards what I would say the more interesting part, which is generative models. So after the Easter break, we are going to start with generative models. But what I just wanted to trigger you a little bit is with some small details. So let me just bring back the Jupyter notebook here and just finish this lecture with a link to generative models. And then after the Easter break, we're going to look into more details here. The basic thing now. So if we look at what we have done till now, we often had supervised data, but we can also have unsupervised data, like with autoencoders. We have data which we treat in what we normally call a discriminative way. So I'm feeding in some information, like an image, and I want my CNN to tell me whether this is a cat, a dog, a bridge, a house, or whatever. So this is essentially what I've been doing till now. And then we train a network to actually be able to make this kind of predictions for us. And then we can discover correlations in the data like we discussed now. But what we want now is to train a probability distribution. And that probability distribution is now going to generate new cats. It's going to generate new dogs, which were different from the training. So we are going to give to the network a data set, and we are going to train a probability distribution. So when we are going to set up a probability distribution, what we are going to have to deal with is something which depends on some inputs X and some parameters theta. So this is what we want now. I want to train a probability distribution, and then you need to make a model. There's always a model. We can't escape that. That model will depend on some function, f of x, of theta, divided by some normalization constant. So for those of you who are familiar with the statistical mechanics, we often call this a partition function. This depends only on that parameter because we have integrated away the excess. So this is the nasty part. And you will see that this nastiness pops up in all of these algorithms because we have to find a way to deal with the normalization constant. So this quantity here is normally given by an integral. If this is a continuous variable, you can obviously set up a discrete distribution. So this x lives in a domain, and this is just given by the quantity here. Now, the nastiness comes in the fact that this f is a multidimensional function. And sometimes, even if you know this multidimensional function, it's too complicated to simulate from it. So if you are dealing with, let's say, atomic physics, and you're looking at atomic neon, that if you take away the nuclear degrees of freedom, it has 10 electrons in 3 dimensions. Your probability distribution is a 30-dimensional object. And you see immediately now that when you want to define something like this, you have to find reliable ways of setting up this normalization constant, which in physics is often called the partition function, but in basically many other fields is called the normalization constant. This could be a model which you have and you know how to calculate. And some of you are familiar with the Boltzmann distribution. That's one which we're going to meet after the Easter break. And that will lead to a popular class of generative models, which are called Boltzmann machines. And the parameters theta, which you have here, these parameters are the parameters you want to optimize. So this is when we are now setting up an optimization problem, what we are going to optimize is this probability distribution. So we are going to use something which is called the maximal, what was the name again? No, the maximal estimator, which means that if we assume that these are independent and identically distributed events, then this probability would be the product of all the probabilities. And then what we are going to optimize then is not the product of the probabilities of the individual ones, but the log of them. So for those of you who are familiar with statistical mechanics, the function which we end up dealing with is something which is called the free energy in statistical mechanics. And that's the function we are going to optimize. So there's a lot of, for those of you who come from physics, which I know some of you are coming from physics, you will recognize a lot of the way of thinking here. And these Boltzmann machines were actually inspired by some of the spin models in physics, like the Ising model, which some of you may have encountered. So but you see now the nastiness in the optimization lies in the construction of this one, and you will see tons of ways of dealing with that. So in some cases, you have methods where you have an explicit expression. Some cases, you have methods where you try to estimate it indirectly, and we are going to meet something which are called general adversarial networks, or GANs. That's one way of doing that. The variational autoencoder and the Boltzmann machines are methods where we try to evaluate this more directly. But this is where we will start after the Easter break. So if you have some, if you want to look up some, I would say, basic literature, the textbook by Goodfellow et al., chapter 16 and 18, contains a lot of information. Now, what we, since you also see that we have to evaluate an integral, that means that when we come to these methods, we have to evaluate an integral stochastically. And that leads to the whole family of Markov chain Monte Carlo, or just MC squared. So this is a further complication. So for those of you who are familiar with Markov chains from mathematics or from physics or from other fields, you will recognize a lot of material which just enters the setup of generative methods. And generative methods are the methods which are, how to say, the popular ones nowadays, right? We cannot escape that. So after the Easter break, this is the kind of topics we are going to dive into. But I just wanted to give you the kind of basic overview and where we are going to meet all the vicious items. So the evil here is just hidden in the calculation of the normalization constant. We take a small break. And by the way, with the deadlines, I'm always, you know me by now, most of you, and I've always been very flexible. So if you have problems with Friday, I mean, there's no problem if you want to use parts of the Easter holiday. I actually shifted the deadline. I think I put it to the 31st or the 1st of April. I don't remember. Yeah. The important thing is the insights which you guys get. That's the important thing. Okay, guys, enjoy your Easter break. And we have lab on Thursday.